Hello everyone and welcome back. Today we're going to be looking more at specifically just the electrons in atoms, and we're going to look at electron configuration, shell construction, and how the electrons fit in all these different areas. So if you remember, we had talked at one point how each level of the atom going from inside to out, electrons fill in a certain order. And that's basically what we're going to be talking about today. So let's get started. So Bohr's atom model. After attending one of Rutherford's lectures, Bohr asked him a very important question. And that question was, why is it that the negatively charged electrons are not pulled into the atom's positively charged nucleus? Now, before we answer this question, I'm going to let you guys know on which parts you're going to be taking notes on. This is more of a background knowledge as of right now, so you do not really need to get this. However, on the next slide, the answering of this question is what you're going to need. So he answered that question on basically saying he proposed a quantum model for the hydrogen atom that seemed to answer this question in 1913. And it's based off of kind of what looks a little bit like this right here on this picture. It's kind of what it looks like. Now remember, at any time you need to pause this, go back, rewatch it. You can always pause, rewind, forward, however, whatever works for you. Just ensure that you get what you need to get from this. Now a little bit more on Bohr's atom model. So the electrons move around the nucleus in only a certain allowed circular orbits. These orbits depend on the level that they're at and how much energy they have, depending on their element and how many electrons there are. The smaller the electron's orbit, the lower the atom's energy state is, or the energy level. So the closer it is to the atom, the lower the energy. The further from the atom, the more energy it has. And the larger electron's orbits have a higher atom energy state or energy level, as I just mentioned. Now let's look specifically at the energy states of just hydrogen. Hydrogen is a perfect example because it has one electron and one proton. So Bohr suggested that the hydrogen atom is in the ground state, also called the first energy level, when the electron is in the n=1 orbit. In the ground state, the atom does not radiate any energy. So this is as close as the electron is going to get to the nucleus itself. It cannot get any closer than this point. And when energy is added from an outside source, like we had for the flame test lab that you guys just did, the electron moves to a higher orbit, such as N2 orbit, and the atom is said to be in an excited state at that point. After that, in order to return to the ground state to be more stable, remember, all atoms want to be stable, the electron must drop to a lower energy orbit by releasing energy. How does it do this? Either through heat, through light, but most of the time it's going to be light. So hydrogen gives us 4 different colors when heated, and Bohr correlated them to 4 different energy level transmissions. It's kind of what we had seen with each of the different elements, even though we only saw one color. And Bohr's model explained hydrogen's observed spectral lines very well. However, it failed to explain the spectrum of any other element. So some elements, the spectrums are so much more diverse compared to what it has for, let's say, hydrogen itself. Now here's a look at the quantum mechanical model. So this model is used to estimate the probability of finding an electron within a certain space around the nucleus. So there are specific energy levels. The ground state, or at least the closest to the nucleus, is n=1. And then you can go up to N2, N3, N4, and so on and so forth, up to about N7 and 8. N8 is a little bit questionable because we only go down to 7 periods, which has 7 different levels for electrons. within each of these levels are called sublevels or subshells or shells. And they each have a different shape. They each hold different numbers of electrons. But we're going to look at what each of those shells are, and you're going to need to know each of these shells in each of these levels. So in the first shell, so n equals 1, has one subshell, and we call that 1s. So it's the 1s shell. Now let's move up to the next shell, n equals 2. So that shell has two subshells. It has 2s and it has 2p. That's for the second shell. The third shell, n equals 3, has three subshells, 3s, 3p, and 3d. And same thing for the fourth shell, n equals 4, has four subshells, 4s, 4p, 4d, and 4f. Now, when we say and so on for this point, we only have these four different shells, s, p, d, f, s, p, d, and f. Those are the only types of shells that ever occur on atoms. Those are the only shells. Now, if we were to write it out here, you could see, and I don't have anything in this, but this would go kind of along with what we have done. So here in energy level 1, we have subshell 1s. How many orbits there are? There are 2. So what I want you guys to do is, based on my verbal, I want you to write down each of these sections. So subshell 1s. The number of orbitals, there's only one orbital in this one. And, sorry about that. And the number of electrons that you can have here are 2. So you have the 1s subshell, the one orbital with 2 electrons. Now compare that to N2. You have 2 subshells, so 2s and 2p. The number of orbitals it will have will actually be 4 here. So you have a 2s and 3 2p's. So 2p, 2p, 2p. Number of electrons here would be 8. 8 electrons. So I'll say that one more time. 2s and 2p. And here you're going to have 4 orbitals. 4 orbitals. And then you're going to have 8 electrons. In shell 3, you have subshell which has 3s, 3d, and 3p. So that is a total of 1 subshell for s, 3 for p, so that's 4, and then d has 5. So that is a total of 9 shells, which means that you have a total of 18 electrons. So I'll say that one more time. 3s, 3d, 3p, and then your number of orbitals is 9 with 18 electrons. Now if you guys notice, there is a correlation. The number of orbitals corresponds to the number of electrons divided by 2. So however many electrons you have, divide that by 2, gets you the number of orbitals. The number of orbitals multiplied by 2 gets you the number of electrons. Now, n to the 4 is a little bit more, where you have 4s, 4d, 4s, 4d, 4p, and 4f. 4s, 4d, 4p, and 4f. So the number of orbitals there is the 9 that we had for 3, but we're going to tack on another 9 orbitals. Yes, another 9 orbitals. Sorry, 7 orbitals. 7. So 7 orbitals. So a total of 16 orbitals here in the n equals 4, which means that we'll have 32 electrons in the fourth shell. So I'll say that once more. 4s, 4d, 4p, and 4f with 16 orbitals. 16 orbitals and 32 electrons. All right, moving on. So electron configuration. The arrangement of these electrons that we had talked about in an atom is called the atom's electron configuration. There are three basic rules or principles used to define how electrons can be arranged in an atom's orbits, in each of the orbitals. That goes along with the next rules that we have actually on the next slide. These are part of some of your definitions that you had, like Afubu's principle and a couple others, which we're going to get to on the next slide. So let's start with the rules of electron configuration. The first rule, I always pronounce this wrong. Aufbau principle states that each electron occupies the lowest energy orbital available. That's it. That's Aufbau's principle. It states that the electrons occupy the lowest energy level orbit available. So it wants to be as close to the nucleus as possible. As close to the nucleus as possible. That moves on into Pauli's exclusion principle. So Pauli described that there can be a maximum of 2 electrons that may occupy the same orbital, but they only can do this if they have opposite spins. So sometimes you're going to hear there's an up spin and a down spin. So when you have an up arrow or a down arrow, so up spin, down spin, up arrow, down arrow. This is something you're going to work on the activity for tomorrow in class on electron configurations, on how they are connected. And then this moves into the last thing, so Hund's rule. Hund's rule states that single electrons with the same spin must occupy each equal energy level before additional electrons with opposite spins can occupy the same orbitals. So this kind of goes along with one of your activities that you have tomorrow, and this deals with, let's say you have 2 hogs, and they don't like seeing each other, but they stand being in the same room as long as they don't see each other. So you can have one facing in one direction as long as you have the other one facing the other direction. But if you have multiple rooms, like say you have 2 rooms, well, you can split those pigs up and have one in one and one in the other. So you can split those up, meaning each electron will fill the shells one by one in the same energy level until they have an equal number, and then they start filling again. Now, here are how each of the blocks work. So these are called sub-level blocks, and it shows you how each energy has a different way of recording all this. So you have the S block here, which is the first 2 periods, first 2 groups. So the first 2 vertical groups. So you got the S1 and the S2. Then on the opposite side, the last 6 groups, you have the P block. So you have P1, P2, P3, P4, P5, P6. In between the S and the P, you have D, and then you have F at the bottom. So make sure you guys write these down, that you kind of have a general sketch of this. So you got S block, you got P block, the D block, and the F block. Moving forward. So let's do a learning check. So using that periodic table, write each of the complete electron configurations for each of these. So based off of this sub-level block here, we're going to go through each of the elements to determine what it is. So we're going to look at chlorine first. So chlorine is number 17 on the periodic table of elements. If you look at it on the board, you can see that it's in group 17, which means that it's going to be part of the P block. What does that mean? That means that's the end of its electron configuration, how you're going to write it out. So I'm going to show you guys this. So this is how you would, in essence, write it out. So you guys start out with filling it from left to right, starting with the first blocks. So you got the 1s. So 1s2, we filled it up to 2. 2s2, 2p6, 3s2, 3p5. I'm going to go and I'm going to cut the video here, but stick around because I'm going to add on another video showing you guys how I would figure this out through what's called the diagonal method. So stay tuned, and we're going to flip over to the diagonal method. We're going to take a look at how the diagonal method works here, and we're going to look specifically at how can we figure out to write the electron configuration for chlorine. So chlorine is one of our elements, and it is element number 17. So if you look at a periodic table, it has the atomic number of 17, and we're going to utilize this as helping us in order to determine the electron configuration. So when I was talking about dealing with the electron configuration, there's this thing called the diagonal method. So in order to figure out the diagonal method, you need to write out a format like this. So you're going to have, if I can erase this, you're going to have 1s, 2s, 3s, 4s, 5, 6, and 7. At 2, you're going to start putting p's. So you got 2p, 3p, 4p, 5p, and 6p. But we're going to stop there. Then you're going to go over to 3, because remember, we were talking about orbitals. So 3 has the d orbital. And then we're going to put 4d, 4d, 5d. We're going to stop there. And then we have 4f, 5f. Sorry, we also need to make sure that we have 7p and 6d. We need to make sure that we have those. So you should have, in correspondings, you should have 7 S's, 5 P's, you should have 4 D's, and 2 F's. The reason for this is if you look at the periodic table, each of the blocks corresponds to specific values. So that's how this connects. Connects to the periodic table, how it's aligned. And when we talk about the diagonal method, whenever we're trying to fill in energy levels, we're going to go at a diagonal like this. So we're going to start from up here. We're going to go down. So whenever we fill in, we're going to start with 1s, then 2s, and then 2p, 3s, and then 3p, 4s, and so on and so forth in this method. Now it's a little messy on my side, but I'll post on Edsby for you guys a motion of the method of this format. So I'm going to go ahead and erase these here so that we can practice this with chlorine. So chlorine has 17 electrons. So we need to make sure that we fill out those 17 electrons based on the format. So I'm going to pause here for 1 second, and I'm going to come back to this in a little while. So don't go anywhere, because it'll be instantaneous for you guys. Okay, so we just finished discussing with the number of electrons for chlorine being 17. As you can see right here, chlorine has 17 electrons. So what we need to do is we need to put every single one of those into a spot. We need to start with 1s because that is our first and lowest energy level. It is a conceptual section that has been agreed with people. So we're going to start with 1s. So what we're going to do is right down here down below, we're going to write the electron configuration. So we're going to start with 1s. Now, we've already put 1 in there. So we need to put a second one in there because we have 17 electrons. So what we need to do is we need to put a total of 17. So we're going to put a 2 here because we can fit 2 electrons in every spot. Now, some we can fit more than 1. So we just did 1s. So we're going to do 1s. And then we need to go to 2s because 2s is our next spot, 2s. So we got 2s2. Now, right now we have done 2 electrons. We've done another 2 electrons. Now we can go down the next line, which is 2p3s. So we'll write 2p. Now, how many can we fit in 2p? Well, P's can fit 6 electrons if we remember. So let's write a 6 down here because we may use all 6. We may not. We'll see. So we've done 4 so far. So we have 13 more left. So if you guys notice, I jumped from down here to up here. So up here we have 13 left. So what we need to do is we need to subtract that by 6. So 13 minus 6 will leave us with 7. So that's our next number, 7. So 7 is what we have left once we put 2p6. So we've used 6 electrons there. So we have a total of 2, 4, 6, which will be a total of 10 electrons. So we've used 10 electrons. Now, since we've done 7, we can still go to the next one. So we've done 2p up here, 2p. Now we need to do 3s. So we'll write 3s. Now how many more electrons do we have? 7. So let's see. How many electrons can S fit? Well, S can fit 2. So we're going to put 3s2, like a square, which means that we're going to have 5 electrons left, being that we've used 12 electrons total so far. Because 2 plus 2, 2 plus 2 plus 6 plus 2 equals 12. That's what we're looking at here. Now, since we've done S, 3s, now we need to go down the next line, which is 3p4s. So let's write down 3p since that's the next one. Now, if we remember from our previous section right here with the 3s2 and also 2p6, we can fit 6 electrons in total per p sets of orbitals. So what we're going to do is, do we have 6 left? Well, not really, because we only have 5 left. So we're going to put that 5 at top here instead. So that's what we're going to do. So this is going to change from a 6 to a 5, which means we can erase that, and our total comes out to be 17 electrons. Now if you want to double check your answers, just add up your exponents here. So you got 2, 4, plus the 6 is 10, plus the 2 is 12, plus the 5 is 17. Does that match 17 electrons for chlorine? I think it does. So that's how we can do it for chlorine. Now let's do one more. I'm going to show you guys how we can do one more. And this time it's going to be with strontium. So I'm going to scroll down here. I'm going to do strontium. So let's do strontium. We're going to do strontium. Strontium. Strontium is element number 38. Number 38. So it has 38 electrons. So we're going to need to do the same process again. So we're going to do 1s, 2s, 3s, 4, 5, 6, and 7. And then we'll put 2p, 3p, 4p, 5p, 6, and 7. And then 3d all the way down to 6d. Oh, let's change that to a 4. 4d, 5d, 6d. And then we've got 4f and 5f. Now I'll explain to you why it's like this once we get back in class. It's something that I have to talk to you guys in person. But we're still going to use this diagonal method here. If I can show you guys. We're going to utilize this diagonal method here for every single one that we use. So we've got 38 electrons. So we need to make sure we go through those 38 electrons. So we're going to scroll down just a little bit more. And here's what we're going to do. We're going to start writing out. So we're going to do 1s. Now we know s can have 2 electrons. Then we're going to do 2s because it can have 2 electrons. 2p because it can have 6 electrons. So right now we've gotten to 10 electrons there. So let's write down here. So we've got 28 electrons left because 38 minus the 10 gets us the 28. So we have 28 electrons that we need to fill still. And we've done 1s, 2s, 2p. Now we need to do 3s. So let's write 3s. 3s2, because s always has 2 electrons. And then we're going to continue on. We're going to go 3p4s. So 3p6, 4s2. We're going to stop there for just a moment, and we're going to figure out how many electrons we've used so far. So at first we had 10. So we know we have 10 up to here. Let's count how many more we have. 2, 4, plus 6 is another 10. So we've used 20. So let me rewrite this. 4. So we've used 20 electrons so far. So that means that we have 18 left, because 38 minus 20 equals 18. So we need to continue on down the next line. So we're going to go 3D into 4P into 5S. So let's write 3D. Now how many can fit in D? If we remember, we had 5 orbitals. If we have 5 orbitals, that means that out of those 5 orbitals, we can write 10 electrons. So let's put a 10 in there. Because remember, 5 orbitals, if each orbital has 2 electrons, that means that you're going to have 10 electrons. Then we're going to go into 4p. Now, p has 6 electrons max, right? So we're going to put 6, and then we'll write 5s, and we'll leave it there for now. We'll get back to the value here in just a moment. But let's count up how many we have. So we had up to here, we had 20. So with the 10 is 30, plus the 6 is 36, so we got 36 electrons, which means that we need 2 more electrons. Which means that this 5s, how many does s hold? S holds 2. So 5s2, let's write that 2, because that's the maximum number, and that's how many you have left. So that works. So we have a total of 38 electrons. Now you can continue this on with each of the other sections down here in each of these levels. But for today, we don't need those because that's not how high we're getting up to. But in future sections, you will be able to get to those. Now, we're not going to deal so much with the 4F and 5F because those are a little bit more complex with D, the D orbitals. But that's pretty much how you can write the electron configurations. Remember, if you have any questions, send me a message on Edsby. I can answer as soon as I can. I will be available all day tomorrow to answer questions for you guys. So if you have any questions, shoot me a message. I will respond as quickly as I can. Plus, the activity you have tomorrow will go over more of that. But just hang on tight because we're going to go into how these orbitals are shaped. So just stay tuned and you guys will be able to know what the orbital shapes are. I hope you guys understood all the stuff dealing with the SPD F orbitals on how to fill them up and how they can go through the progression. But now we're going to move into how those orbitals are differently shaped in a three-dimensional body. So we're going to start with here. So the orbitals are a three-dimensional space around the nucleus which electrons are most likely found. So here we're going to take a look at that. Each shape represents electron density. It's not a specific path of the electron flow. Key word, it is not a specific path. It is just an area that it could potentially be in. It is not guaranteed. Each orbital can hold up to 2 electrons. So this goes along with our Pauli's exclusion principle. So only 2 electrons per orbital. Now let's take a look at each of the subshells. So we're going to take a look at the S subshell. it looks like a sphere. So S, thinking of sphere, nice and easy. So it's one simple sphere. It is possible for the electrons to be located anywhere around this sphere, around the atom's nucleus, with the exception of right in the center. So down here I have an example of the possibilities of the electrons being in the S shell itself. And this is a sphere shape. Now the P subshell is a little bit different. But continuing on with the S orbitals, depending on which energy level it is, depends on the size of that shell. So you have S1 is going to be your smallest shell. S2 is going to be bigger. S3 is going to be bigger than that. S4 is bigger than that. S5 and 6S are going to be bigger than those. Now let's move on to P orbitals. So P orbitals are basically shaped like two balloons tied together. Nice and easy. There are 3 of these orbitals in a P subshell that are denoted as px, py, and pz orbitals based on just 3 different, a 3D representation. So px is aligned on the x-axis, py is aligned on the y-axis, and pz is represented on the z-axis. So these are higher in energy than the corresponding s orbitals of which levels they are in. So let's say with 1s, there's no p orbitals at all. But once you get to 2s, 2s has a lower energy than 2p does. So remember, higher energy level. Now here's how they would also look on the 3-dimensional graph. So px, py, and pz. Now these can combine together, and we'll get into that on Monday on how these all can combine together. These are how they would essentially be if they were just a normal P subshell. These are a little bit more funky, as I can say. They look like flowers or extra lobes. So they are represented on multiple different axes. So d orbitals have d subshells that are divided into 5 specific orbitals. You have the dx orbital, the dxy, dxz, dyz, dz squared, and dx squared negative y squared. It is funky. You don't need to memorize how they are. You just need to know that they are essentially 4 balloons tied together like this, and they just hold together. This is how they kind of look. Now these have even more energy than s and p orbitals. So remember that. More energy than s and p. And these are how they would look. Kind of funky. Now last but not least, so number of electrons in p orbital. I want you guys to figure that out. So is it 1, 2, or 3? So is it 1 electron? Is it 1 or 2 electrons? Or is it 3 electrons? For number of orbitals for P subshell, is it 1 orbital, 2 orbitals, 3 orbitals? Number of orbitals in 4D, is it 1, 3, or 5? And number of electrons maximum in a 3D subshell, is it 2, 5, or 10? All right, go ahead and check your answers. You should have gotten 1 or 2 for the first one. You should have gotten 3 for the second one, 5 for the third one, and 10 electrons for the last one. All right, one last main thing I want you guys to get from this is valence electrons. We're going to go over valence electrons even more throughout this unit. But valence electrons. A valence electron is defined as the electrons in the outermost orbitals. You have to know this. You have to. This is going to help you with Lewis dot structures when we talk about that next week. And let's take a look. So a sulfur atom contains blank electrons, but only how many valence electrons? Well, we can determine this based on a couple different things. So I want you guys to try to determine these. I'm going to give you guys a moment, and then you can check your answers on the next slide when I head over to it to see what each of them are. So you should have gotten the number of valence electrons is equal to the atom's group number. So that helps you out with these, where sulfur atom contains 16 electrons, but it only has 6 valence electrons. Remember, numbers 13, 14, 15, 16, 17, and 18, those group numbers, subtract them by 10, and that'll get you the valence electron count. Remember, 13 through 18, subtract by 10, that gets you the valence electron count. So magnesium, even though magnesium has 12 electrons, it only has 2 valence electrons. Same thing with strontium. Because it's in the same group as magnesium, it has 2 valence electrons. We'll get into Lewis dot structures on Monday, and then we'll get into hybridization on Tuesday and all that. So, quick overview for you guys. Make sure that you have gotten all the notes on valence electrons, that you got the notes on orbitals, that you got your notes on the diagonal method, and also on electron configuration rules. You need to make sure you know these 3 rules. If you don't know these 3 rules, you will probably not be successful at electron configuration, because this helps you on determining electron configuration. If you guys have any questions, please send me a message over Edsby. I will respond as quickly as I can. And we will also be having a brief overview on Monday, but all the information that you're working on tomorrow in class will help you with working on these 3 rules. So be sure you complete that work, and I will see you guys on Monday. Have a great weekend, and ensure you guys do the work.